equation of motion for a vibrating system, right? Kx is equal to, when we did it equal to 0, that was the free vibration. And then we went ahead and said it's equal to f of t, right? It's forced vibration. But when we said forced, we were looking at a very particular type of force. You want to remember how it was? Harmonic. F naught, it's harmonic, exactly. Cosine omega t, okay? Right. So I think we beat this to death, you know? F naught cosine omega t, and then we figured out if omega is less than omega n, if it's equal to omega n, if it's greater than omega n, and each one has a particular solution. Now, in real life, not every force that acts on something is sinusoidal. So,
What?
Sinusoidal.
Sinusoidal, yeah, or harmonic, I should say. Not every force is harmonic. So you go like, what, did we really waste our time doing just this all along? Well, the question is no. I mean, the answer is no. So this chapter, the author put it as a separate chapter. It's called Vibration Under General Forcing Functions. So in other words, this f of t now is not this. It could be anything. It could be,
A jackhammer
for example,
and a.
it could be, for example, an impulse function. You know, just like you took a hammer and you hit something, right? Remember from dynamics, impulse is force times delta t, right? So how does a system respond to when you hit it like that? Or it could be just a function that's going to look like this. You know, we call this a step function. 0, 0 at time t equal to 0, then you have a certain value. You know, it's almost like you're holding something and then at t equal to 0, you just apply it. Or maybe you apply it at time tau, nothing, nothing, and then you apply it at a certain time. Maybe you can apply a force that is just increasing with time like this. We call this a ramp function, okay? So how do all these functions create a response to a vibrating system? And this is the topic of this chapter, okay? So, of course, you guys are seeing the screen there, so,
As usual, your notes are more friendly than this.
so we're just gonna talk about just the bit of 7 sections with each one. I concatenated those a little bit. So we'll start with an introduction first, and then we'll talk about response under general periodic function. So this is where we're gonna come in with here. Obviously, this is harmonic, right? And we talked in chapter 1 about periodic force. Is a periodic force a harmonic force? Sometimes. Is harmonic force a periodic force? All the time. So a periodic force is just something that repeats every period, right? It's not necessarily a harmonic. For example, a function like this, you know, that's periodic force. Something like this is a periodic force, etc., etc. So we're going to pay special attention to periodic force in the second section. Then we'll talk about response under a periodic force of irregular form. So that means it does not really, you cannot put in a function to describe it. And then we'll go on to something more complex, which is called the non-periodic force. Like
The
these
ramp
forces,
function?
like the ramp or the step or the impulse functions, you know, those are not periodic functions. And then we'll mention something about a convolution integral, you know, a very kind of interesting way of how these things are actually taken into account. And then look at the response spectrum. In other words, what is the response for the different frequencies, and then end with Laplace transform. In fact, Laplace transform is a good way to solve these kinds of problems, which we'll look at the end. Okay? So my goal, by the way, is to work on this. Of course, we're going to do a little part, and we'll finish it next week. and then the week after, we'll start doing a little bit of 2 degrees of freedom systems, you know? So when you have 2 masses now that are all linked with springs, how are you gonna analyze it?
Probably simplifying.
And then we'll talk about modes of vibrations, because now how many frequencies are you going to have? Each mass is going to have its own frequency. Now, 2, if you have 3 masses, you're gonna have 3 frequencies, etc. So it gets, so, again, in many practical problems, we have forcing functions, as I mentioned earlier, that in real life, they are not always harmonic, right? So you need ways to figure those out. So those forces could be maybe periodic, or they could be non-periodic, and we need to find out how we analyze those. Now, there is one theorem that we talked about at the end of chapter 1. When you have a periodic function, can you turn a periodic function into cosines and sines? Yes. Remember, the rule is Fourier series expansion, right? We learn that in math all the time. Each function that is periodic, you can actually expand it as an infinite sum of cosines and sines, okay? And we'll come back to that in just a second. And if you take a periodic force, you know, through Fourier series, I'm just going to show you the concept because we're not going to do this. Periodic force Fourier series, we're going to get a bunch of cosines, right? And sines. And these are harmonic forces, right? Harmonic forms, right? But we already know how to deal with harmonics, right? So how are we going to get the response? So the response will be simply the response of the different members of the different terms making up that sum. So if I have, for example, f of t is equal to, let's say, a0 plus a1 cosine omega 1t plus a1 plus b1 sine omega 1t, and this is just as a demonstration, plus a2 cosine omega 2t plus b2 sine omega 2t plus etc., etc., etc. So what I'm showing here is how a typical periodic function is described in terms of different sines and cosines, right? So if I have a function like this, and let's say I truncate it right here, right? So the response to this, do you agree that it will be the response to this, plus the response to that, plus the response to that, plus the response to that, so it becomes just a big nightmare because you are solving those problems separately, right? This is just a force that has 0 frequency. This one is with frequency omega 1, and omega 2, omega 2. So you get the response to this, right? I call this R1, a response to this, R2, a response to this, R3, R4, R5. And then the total response, right, which is going to be x of t, will be equal to essentially R1 of t plus R2 of t plus RT of t, etc. I mean, that's kind of the scheme of things when we deal with periodic functions. That's why it says here at the bottom, using the principle of superposition, if a forcing function is periodic but not harmonic, it can be replaced by a sum of harmonic functions using the harmonic analysis procedure, which is Fourier series. And then using the principle of superposition, the response of the system can then be determined by superimposing the responses due to the individual harmonics, okay? So conceptually, it's not really a problem. Now, so for periodic forces, that's no big deal. The problem comes when you have non-periodic forces, okay? So the response to a system subject to any type of non-periodic force is commonly found using something called the convolution integral. Convolution integral, which we will define later on. I don't think we have time to do it today, but eventually. And then Laplace transform. and of course numerical methods. We're not going to do numerical methods in this class, okay? So we're just going to look at the two analytical methods, okay? So when you have a force that is non-periodic, in other words, mx dot dot plus cx dot plus kx equals f of t that has nothing about a period, nothing about stuff, then we have to use either one of these two methods to figure out how to get the solution. So the two methods are analytical ones, in which the response is expressed in a way that helps studying the behavior of the system, and we'll get to that. And then the other one is just a numerical method, which is typically done in numerical analysis, which we're not going to do. So that was the first section, just to give you an overview of what's going on. This one I already pretty much explained. When you have, for example, a periodic force, right? And an external f of t is periodic, that has a period 2 pi over omega, it can be expanded in Fourier series as this, as you can do in here, right? F of t is equal to a naught over 2 plus sum of j1 to infinity of aj cosine j omega t plus bj sine j omega t. Now you look at this function, you go like, that looks interesting, but really what is a naught, what is aj, and what is bj, you know?
The integral, that whole
So
thing.
that means you have to calculate those by doing those integrations, okay? And when you take math courses, that's what they make you do, right? You guys remember, they make you calculate those coefficients, right? Which we're not gonna do here, but the idea is that once you get this, then this f of t that is on the right-hand side can be replaced by, you know, essentially a naught over 2, right? Plus the sum of ai cosine omega t, right? Plus sum of bi sine omega I. Okay. So once you have that, then the response of systems under general periodic forces is considered, in this case, for both first and second order systems. As an example here, first and second order systems. As a reminder, what's a first order system? Right? Remember, it's all about equation of motion. What's the highest derivative, right? This guy is a second order, right? The highest derivative is the second, but there are some first order systems in which the highest derivative is the first derivative. Example. Take a look at this one here. These are examples of first order systems, you know. Take a look at this. What is the equation for that? It says cx dot plus kx is equal to ky of t. Why is it a first order system? Because obviously the rigid mass here, if you are looking at the point B, how the point B is actually moving, right? Because this is what you are trying to solve for, x of t. What are the forces acting on this guy? Obviously there will be a cx dot in here, and then it will be a k times the difference between these two, which is x and y, right? When you rewrite that equation, what are you going to get? Cx dot plus kx plus kyt is equal to 0. Is equal to kyt. That's first order system, okay? We don't need to rederive any of this. This is just showing examples of first order systems. Usually when you have those is when you have kind of zero mass. Why? Because that's the mass that's, if you put this one as mass as 0, this term does not exist anymore, then you just end up with the second order, with the first order. Obviously for second order, we are all familiar with this, right? Spring mass system, right? And anytime you have a mass, because it's equal to, sum of the force is equal to mass times acceleration, that's the second order term there, okay? So those are just examples of first and second order. Now if you look at that first one, the first example we were looking at, and you consider the spring damper subjected to a periodic excitation, right? In this case, what do we have? We have Cx dot. In fact, if we move that point B, if we do a free body diagram of point B, and point B is moved down a distance x, right? And remember, this is the ground, right? So what kind of forces would be acting on B? Well, if it's moving this way, obviously there will be a force acting in this direction, which is called Cx dot, right? Because remember, it's a damper, so it always goes opposite. And then here you have a spring that at the top, it moves with y of t, and here it's moving with x of t. Now, is that pushing on this point or pulling on that point?
Pushing.
Always pushing?
Well, if the force is pushing down, the spring is, oh,
Well-
it's pulling up, sorry.
Well, it I think you can tell, it depends. If x is more than y, right? In fact, if x minus y, let's look at x minus y. If x minus y is positive, that means the spring has
Stretched, right?
stretched. And if it has stretched, that means what is it doing? It's pulling on stuff, right? So you can maybe do this, k x minus y. Because if x minus y is negative, that means it has compressed, right? Then it's,
It's got more potential
that
energy.
means it's pushing on stuff. So here you have then Cx dot, minus Cx dot minus k x minus y is equal to mass times acceleration, but there is no mass, as it's indicated in here. It says rigid bar, no mass, so it's going to be just equal to 0, right? So what do we end up with in this case? I just multiply by minus sign here for everything, then it becomes Cx dot plus k x minus y is equal to 0. Remember, a big part of any vibration problem is really establishing the equation that describes this. This step is really the critical step, because you could be looking at that thing all day. If you don't have an equation that describes it, you got nowhere to go. Now, suddenly you say, hey, I have one first order differential equation which I can solve. In fact, because I'm trying to solve for this guy, I could maybe put in the y on the right-hand side. In fact, Cx dot plus Kx is equal to Ky, right? So this is the function that we're talking about, y of t, you know? This is the stuff that is disturbing the x, and you're trying to find really what x is. Except that here you don't know what y is, you know? You don't know what that function looks like. So what you could do, you could say that if we divide everything here by c, we're gonna end up with an equation that's gonna look like x dot plus, as the book writes it down, some ax is equal to b, what's equal to ay,
And then,
right? Now, clearly from here, you know what a is, it's simply k over c, right? As indicated there. And,
so they equate it to that other,
right, now
Transform.
you're taking this function and you're saying, okay, now I better rewrite this as a Fourier series expansion, you know? So you're gonna have some value plus a bunch of sines, or a bunch of cosines and a bunch of sines, okay? So when you add those up, then finding the solution would be simply a solution that is associated with each one of them. This is just as an example, right? We don't need to go deep onto this. This is the first order, just that same problem that we talked about before, right? Where the value of A now is equal to 1.5, right? Is equal to, here it's the not Taylor expansion, but the Fourier series expansion, in which we are only taking the first terms. We're truncating it just in the first 3 terms. So there's a constant, something multiplying a cosine, and something multiplying a sine. Okay, how do we find the solution to this? The solution to this will be equal to the solution that is brought up by just 7.5. And then we do the solution when it's equal to just 4.5 cosine omega t, cosine t, we get the solution for that. And then we do the same solution just for this term, and then we add them up. You know, you see how painful it is, but conceptually it is easy. It's like, hey, I'm taking the contribution of each one separately and adding them up, okay? So the equation of motion of the system is given by this. The first solution will be what? Then what do? You just say, I'm just gonna first look at what is the contribution of the 7.5 on the slope. Okay, so you solve for this, okay? You solve for that, and then you solve for what? You solve for the first one, I think you just get the answer as xt is equal to 5. Because clearly, you can come back to this, I mean, what is the solution to this problem? You know, the particular solution will be x equals 7.5 divided by 1.5, which is 5, right? That would be a solution. And then you do the solution for x equals 4.5t, and we know how to do this, right? And in this particular case, we just say it's y cosine t minus phi, and then from there we get the amplitude y, and then we get the phi angle, you know, just by replacing the condition here. And then we repeat the same thing for 3 sine 3t. We get the solution for that. And then at the end, what do? We just add them all up. All I want you to understand here is just the concept, you know, it's not like we're gonna, if you have, we have done f naught cosine omega t. What I'm trying to say is that if you have more than one term in here, to find the solution, you have to find the solution for this, and then for the other one separately, for the other one separately, and then you get all those 3 pieces or 4 pieces, however many you have, and you add them up, okay? That's how you treat the periodic side of the function. In fact, here is a graph that shows the forcing function. See this forcing function here in dotted thing, right? This is that forcing function that is equal to, what is it equal to? It's the sum of 7.5 plus 4.5 cosine t plus 3 sine 5t. If you plot that, that's what you get. You get that dotted line right here. That means it's the forcing function. And then here, what do we have? The first 2 terms of x of t. That means it's the 5. The first 2 terms, that means this term and this term, you know, the sum of these 2. And then if you need the 3 of them, then it will be 1, 2, and 3. All right, so that takes care of at least conceptually what it is. And this is the solution for just the first 2 terms. And then the solid line in here that you see is the solution using all 3 terms. Okay. Now, if that's for a first order system, what if it's a second order system, such as something like this? Spring, mass, and damper, that is under the action of a force F of t. In this particular case, if this force F of t is not harmonic, it is just periodic, that means it can be rewritten in this particular form through the use of Fourier series. So it's going to be some average value plus an infinite sum of cosines and infinite sum of sines. Okay? So what do you do with that? To find the solution, obviously, the solution will be the solution, the final solution will be the solution for A not 0, plus you have to add the solution for each one of these terms and for each one of those terms. Okay? That's why people do not do this by hand, you know, because it becomes very calculation intensive. In some cases, if you don't have the function very well defined, you have it defined in piecewise, then you use the discrete form of the Fourier series, which will allow you to do this numerically.
So next week we'll be programming this into MATLAB.
We'll be doing something different actually in MATLAB, but related to this, yes.
Okay.
Now, moving on, you see how we're already in section 4. Because all these first 3 sections were just the concept, so this is the interesting part. When the function is non-periodic, okay? When the exciting force is non-periodic, then, for example, such as due to the blast from an explosion, or you hit something with a hammer, or whatever, a different method of calculating the response is required, because you cannot use Fourier series then. It's not a periodic force, so you're stuck. It's not harmonic, and it's not periodic, you know? So what do? Now we have different methods that we have to do. So various methods can be used to find the response of the system to an arbitrary excitation. And we can, for example, represent the excitation by either a Fourier integral, convolution integral, or Laplace transform. And I think we will concentrate more on the convolution and the Laplace transform as we go forward. See, section 5.
You really wanna get our brains into this right now before we do the test?
Well, we'll just, still got another 15 minutes.
Yeah, okay, just checking on you.
Just to kind of get you to think about it, so we can pick it up next week. The exam is not going to be hard, I tell you.
2 lines?
Yeah, why you would do
Two lines, wow,
Every
yeah.
time.
I think you said that
I
every
agree, I'm with you.
Yeah,
That should be the thing.
so
I hope you're right.
just don't rush and try to finish and do it the first time and say, yep, here it is. And then you go back.
That's what I did last time.
Yeah,
that's
Chris,
what I
don't
did
do that.
last time.
Please
I
go
did-
back.
I
No,
did-
you're talking about me.
Okay?
That
As
was
long as
me.
you got the time, and I'm not pressuring you to finish.
Yeah.
I'm not telling you that you have to finish by 6 or 7 or whatever.
It's so relaxing and enjoyable just to be in the moment for the test. Why would you want to rush it?
I'm staying till
No, I
10:30.
just want to get through it. It's so painful.
All right. A couple of interesting things in here. Maybe I should stop on this one. I can tell that your mind is probably not going to be in it, in the convolution.
How you can tell that?
Right, so we'll pick it up from here next time, because there's no sense. We'll have to remind you a few things about dynamics from dynamics, when we talked about the impulse equation, right? So.
And that
then
is on the
we'll get
FE
it from
exam.
there. So at least we know where we are in here, so. Okay, so.
Are you
with that
sending these
said-
slides out? I noticed
Yes,
they
I
were on
was
the-
trying to, I'm gonna try again now to see if, I was trying all afternoon, and I couldn't. Because Canvas is.